Good morning. Welcome to this morning's session. Thanks a lot to VELUX for putting this together. This is really the best daylighting event, I think, that is being organized this series. It's really the only opportunity for me to meet with all our colleagues from Europe again, and I thank you a lot for putting this together. This is really fantastic. And with the theme of today's conference is New Eyes on Existing Building. This is the Great Dome at MIT, and it was oops, I gave it away. So basically below, the Great Dome had been closed since World War II in some fear of some German submarines during World War II. The dome was closed. And there was a fantastic library below here, the Baker Library, and now it was recently, let's see, that opened again, and so it's this fantastic space again, and this is what we talked about yesterday. The costs for this were absolutely gigantic, so we will never get the savings back. But just because the space wasn't used at all, and now it's completely filled with students working, enjoying the daylight, so I think this just speaks for itself. This is Sustainable Design Lab. This is intoxicated students after we released our new software about 2 weeks ago. And what really the goal of our group is we want to change current design practice. And the way we do this, we look at how designers and urban planners work, and then we try to implement workflows that are respective to their workflow, but give them extra information so that they can improve their designs as far as comfort, daylighting, energy use, and so far is concerned. So today I'm not only going to talk about the Lorax project. I have way too much material, so I rushed through daylight availability, our new work on glare, and expanding towards our urban modeling efforts as well. So the framework that we've been using now for a couple of years to look at daylighting generally is to talk about 3 different concepts, and I think they should be treated independently. There's daylight availability, there's visual comfort and energy, and these are all aspects that are important for a designer, even though, of course, we know that they're interrelated. So once we have daylight available, then, of course, if it's too much or too little, there's a feedback loop. You have to turn on the electric lighting, you get too much daylight. There's certain intervention taking place, occupant behavior or controls, and that has an influence on energy. So how can this look like? Well, there are various levels of how this can happen. There's manual control. This is obviously the European solution, opening, closing windows. You can turn on the light. You can change the shading systems. High occupant satisfaction if it works, very difficult to model. Then you can have automated blinds, and we were in the epitome of the automated building last time. Basically every single blind, it seems like, and it seems to work, believe it or not. Only in Switzerland, basically every little blind system was adjusting independently depending on direct sunlight shining on the window. And then you have the architectural control. This is, of course, great. Buildings like at the New York Public Library, where there are no external controls, and still people are really constrained. Once you're in a library, you sit at your workplace and obviously can't move, really. And they manage with these big windows never to get on both sides the lighting into the space that it's disruptive. So this is a wonderful example where this is, of course, architecturally inspiring. And then we have the other extreme, again, back to Switzerland, where we take out the walls, we take out the furniture, everybody gets a beanbag, and you pick your spot where you want to sit and work, and that, of course, works as well. So when you want to put this actually into practice, how do you look at daylight availability, glare, and energy? I give you a simple example of how we're doing this. Say you have a south-facing office, and you just want to decide, should I use blinds or not? Or instead of blinds, you can use more complex controls. Then the first thing you can do, you can run this annual daylight availability map, and you see, well, how much daylight do I have within the space? And if I don't have any blinds, then 3/4 of my space are daylit. If I have blinds, I'm losing. So the argument would be, well, no blinds. But then you run an annual glare analysis, and then you see this is a temporal map based on daylight glare probability. So 1st of January to the end of December and time of day. If you don't have blinds with such a big window, most of the year when the sun is not too high in the sky, people are experiencing glare. So this obviously doesn't work. We need some blinds. But, and this is really where this type of analysis starts changing design, you see then that for 3/4 of the year the blinds are closed in a case like this. And this is then basically tells you the story of daylight within the space, that you can't, in this case, see out for most of the year, so then the whole big blind becomes a little moot and pointless. And I would say this is when you see people changing their designs, actually. And of course, the last part is once you know what goes on in the space, you can do an energy analysis. And loads are really boring usually, so you look at costs or you look at carbon emissions, depending if you're in the US or Europe. And the simulation environment that we're using for this is a plugin called DIVA for Rhino, and you can use it parametrically as well. And just as a tie-in one of the last presentations yesterday, students at MIT now in first years learn it's very simple to do parametric analysis, link it to Galapagos, and then you get this very, which is a genetic algorithm, this very complicated forms, which might be your optimum point. So with this little study, we just wanted to show, this is Elliot Glassman's work, well, in how far this deterministic thinking, this is the optimum way. How does that do the buildings look as a result out of this? And we just wanted to show that this is really often, it's really unresolved how that works. So we used these boxes and just said, okay, I'm optimizing for insulation levels, window to wall ratio, and overhang. What's for cost or for carbon my best solution? But then we also changed the climate. We use today's climate. You use climate in 2050, 2080. And what you see actually, that this climate optimized building changes over time. So at the beginning, you have maybe here an R40 and a smaller overhang, and that overhang changes over time. Your R value changes as well. So I mean, the main point out of this is it's very difficult for us to decide what is an optimum point, because do I optimize my building for today? Do I optimize it for 2080? But then, of course, I have uncertainty because I don't really know what the climate in 2080 is, and that leads us to different results. So I think ultimately, that shows that you still have to have strong design, and you have to decide for yourself. As a designer, you have to say, I want to optimize for cost, and you have to be aware of this. Because there's often this fear that the computer takes over design for you, but this shows you that there's a high level of arbitrariness, what you actually pick as your performance metric. So daylight availability, that's a study that we've done, and of course, why do you do a daylight simulation? You want to know where the daylit area ends. It's really trivial, of course. My 6-year-old son knows that where the opening in the facades is where the daylight is, but we somewhat want to be able to say, well, this part of the building is daylight and this is not. So how do we make this distinction? For using the metric that Lisa introduced yesterday, using an annual daylight glare, an annual daylight availability metric, we can then say, okay, what's the percentage of the occupied times when I meet a certain level? And then, depending on what that level is, if you want 90% of the time your target level, or more or less often, you get deeper and deeper into the building. So based on matching to 61 spaces, the ISNA, our committee determined that 50% daylight autonomy would be a good level. So in a way, this orange line, now magically the computer tells you, north of it, it's non-daylit, here it's daylit. So I really wanted to see in how far, that's just what the computer and some daylighting geeks tells us. So how does that match how people experience places? So we started first at Harvard to do this little daylight area exercise. And it's very simple. For students, before they learn anything about lighting, we take them in a space that's partially daylit, and we give them a floor plan and just say, well, draw the line where you think the daylighting ends. And the first time we did that was in the Carpenter Center from Le Corbusier, north-facing studio space. So everybody got a floor plan here. Oops. Here are the windows. So the light comes in from here, and then the students just draw the line here. So this student drew the line here. If you do that for a lot of students, you get a lot of lines. So this is our mean line basically going, that we say this is what the occupant said, how deep the daylight penetrates. And when we compare that to the daylighting metric, we actually got really, really close. So in this case, we were lucky, so to speak, that ISNA matched very well for one space, what we were predicting. So great, quickly write a paper as long as it's still fresh. And so on the one hand, we said that's encouraging. On the other hand, I would really say that's surprising that this works at all. Because we have people looking in the space and they see luminances, and yet we do an annual illuminance calculation. It's in a way surprising how that could match at all. But it worked, nice. So then we tried to do it again. This is our Lorax project. So we worked with several schools of architecture and asked them to repeat the same type of exercise. So they all did this exercise, sent us photos of their spaces, their CAD models, student responses, and so forth. And these are the schools that participated so far. So we have 12 schools, and we've done most of the simulation, but it's still in process. So this is what we got, some preliminary results. Well, first where I wanted to go is to say for design, this absolute line I think is a bit disruptive to say Daylit, non-Daylit. This is really not how we think, since there's a subjective component in there as well. So instead, we basically said, okay, let's do a voting scheme. If 3/4 of people say for a certain area within a space this is Daylit, then this is really Daylit. There are always 20% that you can never satisfy any of. And then there's this transition space. So if 1/4 to 3/4 say it's Daylit, then there's some Daylit, some merit to it, and we call that a partially Daylit area, and less than 25% is just a lost case. And now we convert that into daylight autonomy. So this is the ISNA metric for 300 lux, 50%. And here we say, well, if it's 150 lux as a minimum level, this is kind of our transition space. And we wanted to see how well this works. And here you see that mapped out. This is one of the MIT spaces from Kevin Lynch that we used here. Here you see the simulation for the space. Here's the window, so daylit area, partially daylit, not daylit. And here you see the student responses. So it worked pretty well there. I just show you a few spaces. This is University of Southern California, so sunny climate. Karen Kensick did this work for us in this space here. Worked pretty well as well. This is a punched window. Kevin van den Weilemenberg in Idaho worked very well actually here. This is a top-lit space in Miami University, which is located in Ohio, just to throw you off. And top lighting worked okay in this case, and I'm not sure why the skylights didn't work so well. This space didn't work well at all. This was in Brazil. Solange Maria Leda worked with us there. It's a circular building, so it's this building here, top floor. And here it really might be that this concept collapses because people stand in the middle and they see the luminances and they don't really see this flirting illuminances that we are modeling actually. But when you take all of this, so this is what we got here, not so great. If you look at all of it together, it's pretty encouraging. So what we are doing here, we're comparing for each space partially and fully daylit according to a simulation and according to the student responses. And of course, if it would be perfect, it would all lie on the identical line. Then we would know exactly what people are going to say. It's not going to happen, right? But if you look at it, we can actually mostly say within 10% how big the daylit area of the space is. And that's very good because this is the kind of thing that metric systems might want to have. So we can, within 10%, predict how much of a building will be daylit according to that. So this is so far we are with this study. I think it's pretty encouraging right now. And it seems promising for rating system. As a caveat, we didn't consider dynamic shading systems, but mostly these spaces didn't have any. So a little more on glare analysis, and I rushed through that. So basically, this is something that probably, well, all the researchers know that this is old work 10 years ago from two people in this room, Jan Wienold and Jens Christoffersen, who introduced this daylight glare probability, which is an algorithm that you run on a scene, either a high dynamic range photograph or on a simulation that predicts the likelihood of people experiencing glare. The thing to remember, it's based on two concepts. It's based on the idea of vertical eye illuminance, similar to the work of Miriam Aries, so how much light you get in your eye, plus a contrast ratio. So how much contrast do you have within the field of view? So the first thing, we just compared this to all the other metrics that were out there. That's again a little older, where we basically for the side-lit space said, well, depending on which way you look, where do you experience glare? Here we found that daylight glare probability detects the window as the culprit, whereas all the other metrics think the glare's in the corner due to the contrast ratios. So this seems to be the only metric that yields something plausible. What we did next, because we want to use this concept for simulation practice, we said, well, how do people behave? If you would be in a space like this, if you stoically look forward, then you will experience glare pretty often within a year. But then we said, well, if we allow people to move around, say we have better furniture layout, of course, if you look that way and you experience glare, well, don't look that way, right? That's how we behave in reality. So once you start introducing this, you see how you can get rid of a lot of glare. So if we will look constantly forward in this space, you get glare for most of the year. Once you allow this adaptive freedom, you get glare solved a lot more. So that was the concept. 5 minutes, oh God. So this was the concept, what we tried to do then to test it in an actual field study. So we used Ganthal in 2011, and our students there are about 500 students that sit on 5 levels in this big glass box, basically. And we promised them coffee in exchange for their opinion of their workspace. And we got 100 responses back, and about 30 of the students had problems with the electric lighting due to glare. We took that out because we didn't want to consider that. So we looked at 67 student responses. This is our radiance model of the whole space. So we knew exactly where a student was sitting. So we basically tried to map what students said about their space with simulations. And what we found when we used daylight glare probability annually by itself, that didn't work very well. So what we started after a while, then we said, okay, glare can be multiple things. It can be DGP, discomfort glare. It's monitor contrast, so even if I don't have discomfort glare, if I look at my monitor and can't see, that's a problem obviously as well. And it can be direct sunlight near the workspace. So when we used all 3 of them together, we actually got some good results. So these are some very cool maps from Olsen Jakubiak, who is a doctorate student at MIT. So here you see the 5 different levels. And wherever it's gray, they're basically overlapping levels. And it's a pretty complicated, rich graph. So the inside color always tells you if a student in morning, noon, or afternoon said how he felt between comfortable and glary. And then the outside is always our simulation results. So when the colors map, we predict it right. And basically, in this case, in the morning, the exact prediction we managed in 40% of the cases. But since there's a big subjective component, we said, well, we are happy enough if we are within 1. If somebody says it's intolerable and we say, well, it's disturbing, that's close enough. So in that case, we would get within 70% of the evaluations. And for noon, the noon case, we get 85% of the results right. And in the afternoon, we get 87% of the results right. So I think this is really a step forward in our standing, our ability to predict discomfort glare within spaces. And that's the last part. I have 3 minutes. So urban modeling, I really wanted to show where we are going next. So we developed basically a DIVA for the city, and you can download that here, urban modeling. We call that Umi. And what it does, it's an urban modeling platform for energy, daylighting, and walkability. So the way it works, you set up a massing model in Rhino with your massing buildings, with trees and a street network. And then we auto-export this into Energy Plus for thermal analysis, and you get basically this color maps of energy use intensity throughout your city. The next thing that you can do is, we want to do a daylighting analysis, but we don't want to wait 2 days. So we are basically combining outside DaySim simulations with our own interior light solver. This was done by Timur Dogan, and this published in this paper last year. So that allows us to do this. We can basically do a climate-based simulation of a whole city in 30 minutes. So the way this works here, you see continuous daylight autonomy. Here's the IDS&A metric. It allows you to very, very quickly basically say what the percentage of your city is that's daylit. And outdoor comfort is something that we're looking in as well. Since we know the temperature and the radiation distribution, we can look at heat spots or cold spots within an environment as well to tell you how to react there. Urban transportation, we started off with the walk score that we talked about a little yesterday. So we have these buildings with their usage. We add a street pattern as well as certain amenities, and then we can calculate how walkable the neighborhood is. And we also have our little finance model that was developed with John Macomber from the Harvard Business School. So it's a first order money in, money out kind of thing for a city. So we, of course, with our Rhino model, we have kind of a mini city BIM model. so we can extract construction cost. We can simulate the operational energy use. And this is something that might be interesting to the audience. So this is John is a professor in real estate finance. He basically said, okay, you get a rent, and if it's a Daylit space, you probably get a higher rent. So we basically have this fudge factors in there where you can say, well, how much higher do you think the rent is? And I think that is stronger than productivity because that's always, I think it's always a little lame, these comparisons, because you can get to enormous numbers there, but you don't have really any basis that I've seen. Maybe the next speaker has some better basis, but I think it's very vague. Well, everybody can think about rent. You look at the space, am I going to pay $2,000 instead of $1,500 for that? That's something, well, the market shows you if you're going to pay it or not. So in the end, we get something out of it like a city scorecard. So you automatically get now the density of the city, your cash flow, and this should be 10. So on a good year, you should get 10% of your investment back. Energy use intensity of the city, the Daylit area of your city, the walkability of your city, and the comfort indoor and outdoor of your city. So, and I don't think I'm running out of time. You can go to the Cambridge Solar Map, and we made, I think, the biggest radiance model that was ever built was 17,000 buildings. So using radiance, we basically used the city of Cambridge, used LiDAR data to build a whole three-dimensional model of a whole city in radiance, and then we ran DASIM on the whole city to get annual irradiation maps, folded with temperature, information for every hour of the year. So based on the composition of the roof, we know how hot the roof gets. That allows us to say the efficiency of the solar cell, which allows us then basically, for every house in Cambridge right now, if you Google the address, it gives you an analysis of efficiencies. And that is my last slide. So summary, I think the Daylight autonomy metric as currently promoted by the IESNA, that is something that can be recommended for rating systems. I think it's definitely something that the Europeans should consider because the simulations are pretty simple, and as Lisa said, there are a number of tools that can calculate this kind of, do this kind of analysis. I think successful glare analysis will require us to run a series of parallel simulation comfort tests at the same time. So contrast ratios, no sunlight near the workspace, DGP, all has to be considered at the same time because one is obviously too much already. And then we obviously see daylighting analysis expanding to the urban realm. Thank you.